All right, so we are going to be talking about planes in this particular unit, and we're just going to start off with a warm-up, kind of like an introductory unit on how lines and planes relate to each other. All right, so let's go ahead with our learning goals. You will understand the basic concepts relating to planes. You will be able to identify 4 methods of determining a plane, and you will be able to apply 2 postulates concerning lines and planes. Pretty simple stuff. All right, so just some basic concepts. You should already know that a plane is a flat surface, but with regards to this, a plane has no thickness in geometry in terms of that. So just remember that it has no thickness. So even though you can see it, it's tangible, it really doesn't have any thickness. Plane is also infinitely long and wide. So like a line goes on forever, a plane goes on forever, but it goes on in every direction forever. Lengthwise and widthwise. Okay, it's often drawn like this. Okay, the arrows represent the plane going on in both directions forever. If you have a line drawn on there, we'll assume, or not assume, you'll be told that points are on a plane, and then if you see a line connecting those points, you can also assume that that line is on the plane. And sometimes you'll have the plane you'll see a letter in the corner. That's just another way to name the plane. Okay, and then again, although the diagram shows a plane with edges and corners, an actual plane has neither. All right, so characteristics of a plane. Let's go ahead and put some lines and some points on there. All right, so now if we looked at this, A, B, S, and T would all be coplanar points, meaning all of those points exist on the same plane. Line AB and line ST are coplanar points, or coplanar lines, meaning the lines exist on the same plane. Okay, segment AB and segment ST are coplanar segments. Points A, B, S, T, and R are non-coplanar points. And that's because you've got A, B, S, and T, and those are all coplanar. However, when you add R into the mix, it is not. So we say that because that one is not, none of them are coplanar, because they would all have to be coplanar. Lines AB, ST, and RP are non-coplanar lines. And again, you have line AB and line ST. Those are coplanar. However, when you add in line RP, it is not, because it clearly passes through the plane. It is not lying on the plane. AB, ST, and that should also be, because these are coplanar segments, should add in here, and RP are non-coplanar segments. Okay, so, and this is, you're going to hear this term a little bit, so it's important to know what it is. The point of intersection of a line, so let's say line RP, and a plane is called the foot of the line. So for example, V would be the foot of line RP, meaning that's the point where it intersects with the plane. Okay, now there are 4 ways to determine a plane. You have learned that 2 points determine a line. So how many points do you think you need excuse me, to determine a plane? You need 3 non-collinear points, and these 3 points can determine a plane. And why is it important that they're non-collinear? And also, do you think more than 3 non-collinear points could determine a plane? Those are some actual really good questions. So let's take a look at just these 3 points. Obviously not collinear, no line drawn through them. If we tried to, we wouldn't be able to make one. Okay, and we could say that those determine a plane. The reason why they have to be non-collinear, imagine I had 3 collinear points. Okay, I could draw a plane that went through like this. I could draw a plane that went through like this, through all those points. Okay, so there's an infinite number of planes that can be drawn through collinear points, which is why it's important that they're non-collinear. So, as far as more than 3 points, well, if I had these 3, we know that they would determine a plane, but if I add in a 4th one, it could be up here. Okay, that 4th one would not be on the plane. So you could potentially have more than 3, but you'd have to be told that those additional points were also on the plane. All right. So that's our first postulate, and it's going to kind of apply to the following theorems as well. So our postulate is that three non-collinear points determine a plan. A plane, we'll add the E on the end here. All right, so now four ways to determine a plane. Three non-collinear points can determine a plane. Again, why is it important that they're non-collinear? Because if they were, then we would have infinite planes going through. Yes, we know that there are more than 3 points. We already went through this. However, in addition to that, a line and a point not on the line can also determine the plane. And the reason why is because, remember, 2 points determine a line. So I could take any two of these points, and that third point would be non-collinear. So it's still kind of going off that first one, because I could just draw a line through C and D, and it's basically still working off that first theorem. Another way, two intersecting lines determine a plane. So if I have a plane and I've got these 4 points, but I connect them with lines, then the two intersecting lines would also determine a plane, because there's only one possible plane that could be determined by two intersecting lines. So keep that in mind. And the last one, two parallel lines can determine a plane, because if you have two lines that are parallel to each other, they can make one and only one plane. So the big thing here is we're going to be thinking quite a bit in kind of like a 3D space, and that's going to be the tricky part of this unit. Now, two postulates concerning lines and planes. If a line intersects, not lines, forget what my typos here. If a line intersects a plane not containing it, then the intersection happens exactly at one point. So if we have this line, and if we have line RP and plane M, P is the point where they intersect. However, if you have two planes intersecting, then their intersection is a line. Because remember, planes extend in either direction forever, so where they intersect would be a line, as opposed to a line in a plane is created by a point, or their intersection is a point. All right, so let's take a look at this example. I want you to go through, I want you to pause it and see if you can answer all these questions. I will answer them for you, so you're not going to be left hanging. But go ahead and pause it, come back. Okay, so the intersection of plane M and plane N would be line AB. Points A, B, and V determine plane M. The foot of line RS in plane M would be P. Line AB and line RS determine, because remember, it's got to have, these two lines have to be on the same plane. So we got A, so line AB and line RS. Both of those are on which plane? And the answer to that would be plane N. So line AB and point, you could have R or S, doesn't matter, determine plane N. Okay, does W, which is right here, does that lie in plane N, which is basically this one right here? And the answer to that is, of course, no. Line AB, so that's this line right here, and line what determine plane M? So we're talking about this plane here. So we're looking for a line on that plane, which would be line VW. So AB, V, so we've got A, B, V, and what are coplanar points? And here you could have either P or W. Okay, A, B, V, and what are non-coplanar points? So since W and P are coplanar, we can't use those. Okay, so we'd have to look at either R or S. Okay, so forgive my markings on the diagram. I had to make some last minute changes because it was labeled incorrectly, but it should be good now. So we are told that A, P, and B lie in plane M. We're also told that CP is perpendicular to AP, and that CP is perpendicular to PB, and that AP is congruent to PB. We need to prove that this, you really can't see this, I know, is congruent to that. So start off with your givens. Now, this stuff up here, the AP and B lie in plane M, that is not going to be listed in your proof. That just allows you to say certain things, or to assume certain things. So we're going to use the given CP is perpendicular to AP, and CP is perpendicular to PB, and that's a given. We're going to use that to say that APC and CBP are right, or actually that shouldn't be CBP, that should be CPB, are right angles. All right, and that's because perpendicular lines form right angles. And then again, this should be CPB. So angle APC and angle CPB are congruent because right angles are congruent. We can then say that AP is congruent to PB because we're given that. And again, this should be CP. It's congruent to CP because of the reflexive property. Then we can say that triangle, look at all these. Glad I caught them. APC and triangle BPC are congruent by side angle side, which would mean that CA is congruent to CB by CPCTC. So really, we're not really doing anything new. We're just learning some new concepts with this. And you just have to think three-dimensionally, and your life will be a lot easier. But it's a shorter section, so we have plenty of time to get through. All right, take some good notes, and make sure you have the examples down with the corrections.